Good morning. We are Jitesh Gupta, Dibakar Barua, and Pranshu Jain from Netaji Subhas Institute of Technology, and we were given problem statement D for phase 1 of the Texas Instruments Analog Design Contest. As a part of our problem statement, we were supposed to generate a square wave using a Schmidt trigger and a triangular wave using a non-inverting integrator placed in positive feedback with the Schmidt trigger. To conduct our experiment, we were provided the Analog Starter Lab Kit by TI. Shown here are the connections to the two TL082 op-amps that we used to implement our given function generators. Along with the Analog Starter Lab Kit provided to us by TI, we used a dual mode power supply and a cathode ray oscilloscope provided to us by our electronics lab. One of the advantages that we had was that the Analog Starter Lab Kit provided to us by TI was very good. The connections were made using jumpers, which were pin to pin and hence very easy to implement. However, it was a little bit difficult to decipher the multiple connections that were present on the board. So we resorted to using the continuity buzzer of the multimeter to check the resistor connections, as shown here. Now we shall physically implement the function generator using the ASLV kit and see the results on the oscilloscope. The connections have been made as shown here. The op-amps have been biased using 10 volts of the dual mode supply, providing currents of 20 and 30 milliamperes as shown. This is the result that we saw on the oscilloscope. The triangular wave provided a frequency of 1.075 kHz and a peak-to-peak voltage of 10.2 volts, while the square wave had an amplitude of 15 volts peak-to-peak. Here is the triangular wave shown singularly, having a frequency of 1.075 kHz and a peak-to-peak voltage of 10.4 volts. Now we shall see the square wave singularly. This has a frequency similar to that of the triangular wave, that is 1.075 kHz, and a peak-to-peak voltage of 15 volts. Now we shall see both of these waves together on the same screen. It is clearly seen that they have the same frequency but different amplitudes. Hence, the square and the triangular waves have been generated on the CRO. The second part of our problem statement made us use the MPY634KP multiplier from TI to use a control voltage multiplied with the output signal to vary the frequency of the triangle and the square waves. The concept used for this was that the additional voltage multiplied with the feedback voltage would make extra current delivered to the op-amp, and since no or minimal current is delivered to the input terminal of the op-amp, more current would be delivered to the capacitor, which would reduce the time period or increase the frequency of the Schmidt trigger. Now we shall implement our MPY634KP multiplier using our ASLV kit and vary the control voltage Vc to see its response on the frequency and amplitude of the generated waveforms. These are the multiplier connections using our jumper wires. Both the multiplier and the TL082 op-amps have been biased using 10 volt dual mode supply, providing 20 and 30 milliampere currents as shown. We begin varying our control voltage Vc from 1 volt as shown. The resulting waveforms have a frequency of 140 Hz at 1 volt control voltage. The peak-to-peak voltages, however, have increased from 13 and 10 volts to 18 and 13 volts respectively. We increase our control voltage to 2 volts, and as we can see, the frequency has increased to 278 Hz, and the amplitude peak to peak voltages have remained the same at 18 and 14 volts respectively, as can be clearly seen. We increase our control voltage to 5 volts. The resulting waveforms have a frequency of approximately 684 Hz. Thus the frequency is increasing as was reasoned earlier, and the peak to peak voltages remain the same with the control voltage. We increase the control voltage now to 7 volts, and we see that the frequency increases even further to approximately 885 Hz. The peak to peak voltages remain the same at approximately 18 and 13 volts respectively. However, increasing the control voltage any further would not result in any increase in the frequency of the generated waveforms. That is, the frequency is saturated after increasing the control voltage to a value of 7 volts. As can be seen, the frequency still remains 885 Hz. We increase the control voltage further to 10 volts, and as expected, there is no change in the frequency of the generated waveforms as well as the peak to peak voltages. Thus, we have successfully implemented our multiplier to vary the control voltage. Thus, as has been documented, we faced a pretty easy situation in carrying out the hardware implementation of our problem statement. Most of the credit for this goes to the excellent analog starter lab kit developed by Texas Instruments. I would like to take this opportunity to congratulate TI on their excellent board, which allows students to carry out analysis of analog systems in a very easy to use manner with minimum fuss.